Hey everyone, so we are wrapping up Unit 4 in our journey through calculus. This video and the next two videos will be focused on reviewing the content of Unit 4. I've hand-selected 19 questions that all relate to the idea of extrema, concavity, points of inflection, critical points, just the whole idea of relating a function to its derivative to its second derivative. So the first video is going to be focusing on questions 1 through 6. And just a side note, you might see in the video, you're going to see some questions pop up with the chart. And the chart is that valuable piece of information, the way to interpret how f prime, and f double prime are related. Some questions you'll see it and some questions you won't. Even though it's intended to be there all the time, I just didn't have room to put it on the screen. So I'll just kind of give you a heads up on that. With that said, let's go ahead and get started with the first question. Number 1, you can see that the graph has h prime there. The given graph is h prime, and it gives us an interval from -3 to 4. And it's asking for when h is decreasing. So the first thing I want to note is this entire unit is going to depend on our understanding of the chart. And if you haven't seen the chart and how it works, you're going to want to go back and look at prior videos of the chart, the calculus chart. It's something that I developed a few years ago, and you can see the relationship between a function, its derivative, and its second derivative, and how those all go together really easily. I'd say it's one of the most important things that you need to know and understand in order to be successful on an AP exam. But I'm going to put the chart up here so you can see it. But the bottom line is, for number 1, it says h is decreasing. We want to know when h is decreasing. So we would say h is decreasing when h prime is negative. Okay. So h is decreasing when h prime is negative. Since we're given the h prime graph, we are looking for when it is below the x-axis. H prime is negative when the graph of h prime is below the x-axis. So in this case, we would say from 0 is less than or equal to x, and then we'd say less than or equal to 4 there. Now, in prior videos, we talked about what's actually happening when h prime is equal to 0, but so you can go back and look at those, but we're looking for when h prime is negative over that interval. It is negative except for when x equals 2, x equals 0, and x equals 4, but those are all endpoints of certain intervals of decrease, so we would just say from 0 to 4. So that's number 1. And kind of want to make a note that everything we do has to be accompanied by a justification of some sort. We want to justify what we're doing because our answer is never sufficient. We have to know where it comes from, and that's very important. For number 2, we're given a table, and I'm going to go ahead and write this table down so I can point to it. We have different values of f prime of x. So when x is -5, f prime is -2. When x is -4, f prime is 0. -3, comma 2. -2, comma 1. -1, comma 0. 0, comma -1. 1, comma -3. Running out of room here. 2, comma 0. And 3, comma 4. So that is a table for different f prime values. And the question is, when is f increasing? So we're looking at f prime here, and we're asking for when f is increasing. So first we're going to justify. So we're going to say f is increasing when f prime is positive. Okay, so that's our justification for what we're looking for. The trick to this is understanding that this is a table of values. It is not an equation, it's not a function, it doesn't represent all x points or all points on the graph, it only represents certain points on the graph. So we have to read the problem very carefully. It says that the derivative, f prime, of a function f is continuous and has exactly 3 zeros. So f prime has exactly 3 zeros. If I look at the chart, I can see that f prime has a 0 at -4, a 0 at -1, and a 0 at 2. So there are 3 zeros for f prime. Well, that's important because if f prime only has 3 zeros and f prime is continuous, that means f prime exists everywhere. That means f is differentiable. In other words, there's no corners or cusps, vertical tangents, things of that nature. That means f prime will never be infinity or does not exist. F prime exists. Since f prime is 0 at 3 specific points, it cannot be 0 anywhere else, and it exists everywhere else. So we would say f prime is positive. We're looking for when f prime is positive. Well, we can see that f prime is positive here and here and here. But what's happening in between these points? What's happening in between x equals -3 and -2? Well, f prime is going to be positive in that interval, because if it was ever negative in between that interval, that would imply that f prime would have another 0. Watch this. If f prime was negative somewhere in between here, then we would go from positive to negative back to positive again, which means we would have 2 other zeros for f prime, and we can't because we only have 3 of them. So that information tells us that where we see values that are positive, that those intervals begin at those zeros. So we can conclude, therefore, that f is increasing from x equals -4 to -1, and from 2 to infinity. Okay? Again, these are the intervals for where we see f prime is positive, which means f is going to be increasing. F prime cannot be negative anywhere in these intervals, because if it was negative anywhere in these intervals, that would imply that we have another 0 for f prime. Same thing here. If f prime was negative for any value greater than 2, that means we'd have other zeros out here. And so that's our 2 intervals for which f prime is positive, or f is increasing. For number 3, we're given the graph of a position, the position of a particle, and it's asking for which intervals the velocity is increasing. So again, this is all about the chart, and we just have to interpret the chart of f prime and f double prime to be position, velocity, acceleration. So we are given the graph of position. So given is the position graph, and we called that x of t, right? And we're saying, when is the velocity increasing? So let's interpret this. Velocity is increasing when acceleration is positive. Velocity is increasing when acceleration is positive. Well, that's all fine, but we are looking at the position graph. So if we interpret this as being our function, and velocity being our f prime, or our derivative of our function, and acceleration being the second derivative, we can see that acceleration is positive when the position function is concave up. So we would say this: therefore, when x of t, or therefore when the position function is concave up. So I'm going to use some notation here just to kind of simplify these things. We would say v of t is increasing when a of t, Well, let me do this. I'm going to interpret these according to what's given here. There's always a good idea here. So v of t, which equals x prime of t, right, is increasing when a of t, which is equal to x double prime of t, is positive. Well, this is true, therefore, we'd say, when x of t is concave up. Okay? So we're just looking for now, since we're looking at the position graph, we're just looking for where it's concave up. It tells us that we have a point of inflection on the position graph at x equals, or t equals 2. So we can see that the position function is concave up over the interval. Therefore, over the interval 0 is less than t is less than 2. And there is no units here, so we would just say over that time interval, the position is concave up, which means the acceleration is positive, which means the velocity is increasing. So this is our answer there. Okay. Okay, for number 4 is actually a calculator problem, and it gives us the function f of x equals 2x cubed times e to the x. Okay, and it's asking when f is concave up. Where is f concave up? Well, again, going back to the chart, let me justify what we're doing here. We would say f is concave up when f double prime is positive. Okay. F is concave up when f double prime is positive. Well, that tells me that I've got to get to the f double prime graph. Now, or f double prime function. Now, some of us might go, well, can't we interpret this through f prime? And we could. We could say f is concave up when f prime is increasing. The problem with looking at it that way is that we're given a function. And so we can't just look at a function and know when it's increasing analytically. We can know when a function is positive analytically. So we want to get to the f double prime graph. And so we're going to have to first take the first derivative. And now notice in f of x, I put a little dot there to represent multiplication, because so many people just do not see the product rule. They see the quotient rule just fine. They see the chain rule just fine. But for some reason, students have a hard time seeing the product rule. The product rule is just when you're multiplying two separate functions. So we are multiplying here. The derivative of a product is the derivative of the first piece, which is going to be 6x squared, times the second piece, so times e to the x, plus the derivative of the second piece, which is e to the x, times the first, which is 2x cubed. All right, so we have our first derivative. We have to get to our second derivative, so we're going to take the second derivative here. And again, now we have actually the sum of two products. And there's different ways that we could do this. I'm just going to go ahead and take the derivative of each of these pieces. So I'm going to use the product rule for this piece first, and then the product rule for this piece second. So the derivative of 6x squared is 12x times e to the x plus e to the x times 6x squared. So that's the derivative of this guy. And then, actually, let me do this so we can see it a little bit, make sure we're on the same page. This was the first function that I did the product rule on. So this was the derivative of all that. And then plus the derivative of this guy. Again, this is another product. So the derivative of e to the x is e to the x, and then times 2x cubed, plus the derivative of 2x cubed is 6x squared, times the first thing, which is e to the x. So then we can see that the derivative of this product is actually this guy, just so we can see that a little bit here. Now we've got the second derivative, and we're looking for when it's positive. I'm going to clean this up a bit by combining like terms, and then I'll be factoring it in a second here, just to make it a little bit easier to work with. I notice that I have a 6x squared here and a 6x squared there. So I'm going to list the highest power first. So I've got 2x cubed times e to the x plus 12x squared times e to the x, okay, plus 12x times e to the x. So that's my second derivative, and I'm looking for when the second derivative is positive. Since this is a calculator problem, from here we could just type this into our calculator and find our zeros, but I'm going to express my work in here to make sure I'm showing work right. So I'm going to write down f double prime of x equals, I'm going to factor out what I can. So I notice I can factor out a 2, an x, and an e to the x, and left over I've got an x squared plus 6x plus 6. And it would be very nice if I could factor that, but that's not factorable. It ends up being, if you wanted to solve it, you could use the quadratic formula, but again, this is a calculator problem. So I have to look for when f double prime is positive. So the first thing I have to do is figure out when f double prime is equal to 0. So we take 2x times e to the x times x squared plus 6x plus 6. And then we use our calculator here to find the zeros. We type this into our y list and then graph it and find the zeros over any intervals that it gave us. It didn't give us any intervals, so we'd be looking for all real numbers here. But the bottom line here, we get x equals, we have 3 zeros. And the first zero you can see right here, okay? So the first zero is 0, and then the other ones were negative 4.732 and negative 1.268. And then of course we have the when x equals 0. So those are my 3 zeros. From here, we're going to look and see what the sign of f double prime is within each of those intervals. So at negative 4.732, at negative 1.268, and at 0, we have zeros. We have zeros for f double prime. So I'm going to put that up here. This is the f double prime information. And down here we have the x information. And if we look at this graph, let's see here, let me pull it up. If we look at this graph, we have, let's see if I can make this work here. We have a graph, this is f double prime, that looks something like this. So this is our negative 4.7-ish and our negative 1.3-ish, right? And we know that it hits these 3 points. And it looks something like this. It starts low, right? And then it comes up, and it goes down, and then it goes down here, and then back up, and it goes up forever like that. And then over here, I think it's kind of approaching the x-axis, so we have an asymptote on that side. So that's what the graph of f double prime looks like. And so we can see the signs are really easy. F double prime is negative for all values to the left of negative 4.732. We can see that f double prime is positive within that interval, negative in the interval negative 1.268 to 0, and then positive for every value greater than 0. And so we go back to the question, and we are looking for when f is concave up, which implies we're looking for when f double prime is positive. So our justification's up there, our work's down here. Just keeping in mind that the number line is never justification. We want to write down our justification in words. But we're looking for when f double prime is positive, and now we can see those intervals. So we'd say, therefore, for negative 4.732 is less than x is less than negative 1.268, and 0 is less than x is less than infinity. So that's our final answer for when f is concave up. Okay. For number 5 has a lot of options here. We're going to have to take a look at each one of these, and you're going to want to read the problem very carefully. Number 5 is giving us some information. It says that g is continuous over a closed interval and differentiable over an open interval. So we remember that there's 3 major theorems that deal with continuous and differentiable functions over intervals. The first one was the intermediate value theorem. Then we learned the mean value theorem, and then we learned the the other way around, I believe. The extreme value theorem and then the mean value theorem. So it gives us some points here. It says that g of 4 is 2, so I'm going to say that this is 4 and this is 2. So g of 4 is 2, and then g of 7 is negative 4. So maybe negative 4 is down here. So we have these 2 points. We know that this function is differentiable over the open interval, which means essentially it's smooth and it never goes vertical. And we know that the function is continuous over the closed interval there. So we're going to just look for which one of these statements are true. And there are multiple answers here. If we look at option A, it's saying that there exists a c value, which implies x, an x value between 4 and 7, such that g of 7 must equal negative 1. So we're saying that it must hit negative 1 for some x value between 4 and 7. And that statement is going to be true. That's a true statement. And that is from the intermediate value theorem. And that's not, I don't want you to start abbreviating it like that, but I want to get through this, review. But it's true by the intermediate value theorem. Since the function is continuous over a closed interval, the function must pass through all the y values between negative 4 and 2 for x values within 4 to 7. So it will hit negative 1 somewhere in that interval. So A is true. B, it says there exists a c value again, such that g prime is negative 1. Well, this is actually dealing with the intermediate value theorem. The intermediate value theorem says if the function is continuous over the closed interval and differentiable over the open interval, then the average slope is going to equal the derivative somewhere. So if I can find the average slope between these 2 points here, then I know that the function will have a derivative that is equal to that slope somewhere in that interval. So I'm going to go ahead and test that. My 2 coordinates were 4, 2 and 7, negative 4. So if I use just the slope formula here, so we'd say the average slope equals negative 4 minus 2 over 7 minus 4. And that's going to simplify to negative 6 over 3, which is negative 2. So since the average slope is negative 2, that means the function must have a derivative that's equal to negative 2 for some value in between there. And option B was saying that the derivative must be negative 1 somewhere. So that statement B is a false statement. It does not mean it's impossible. It just means that it's not guaranteed. And we can see if the function was just a line, just a linear function, then this would be a false statement because the slope for every value, the derivative for every value between x equals 4 and x equals 7 is negative 2. And therefore the derivative can't be negative 1. But we can also get plenty of examples where you would get negative 1 as a derivative. But if you can, remember, if you can show one counterexample, that proves the statement false. So option C now. Option C is going back to the intermediate value theorem. It's saying that there must be a y value that is equal to negative 2. Well, again, negative 2 is between negative 4 and 2. So there will be a x value for which the function passes through negative 2, somewhere between these points. No matter what that curve looks like, if that curve looks like, if it goes up and then down, it has to pass through negative 2. If the function goes down and then up, it has to pass through negative 2. If it just goes straight at it, it must pass through negative 2. So again, option C is true, and that's again by the intermediate value theorem. Option D is going back to the mean value theorem again because it says g prime is equal to negative 2. Well, we just did the work on the average slope. The average slope was negative 2. That means the derivative must be negative 2 for some interval in there. So option D is a true statement, and that is by the mean value theorem. The mean value theorem. For E, it says there exists a c value, an x value, in the closed interval 4 to 7. So there is some x value in the closed interval 4 to 7 for which g of c is greater than g of x for all x values. In other words, this x value is producing a higher point than any other value on that graph. In other words, there is a maximum. So since the function is continuous over that closed interval, we have a theorem that says there will be a maximum and there will be a minimum. So g of c is going to be greater, some c value is going to be produce a y value greater than all the other y values. If this graph was just a line, then this would be the point where g of c is greater than all the other values for the function. If the function went up and then down, then this point is the highest point. This is c, for which that value is higher than all the other values. So this one is actually true by the extreme value theorem. Okay. For option, let's see, for option F, it says there exists a c value for which g of c must be greater than or equal to 2. Well, that one's easily proved wrong. If this function is continuous and differentiable, I can give you just a straight line to prove this. Does g of c have to be greater than or equal to 2 for all values within that interval? And the answer is no. You don't have to have values that are greater than that. So this one is a false statement. For option G, we have another extreme value theorem. It says that there is a value that's less than all the other values. So that is a minimum. That is also true by the extreme value theorem. And then option H here, it says there exists a c value for which g of c is less than -4, less than or equal to -4 for that interval. And we don't have to have values below -4 again. For the same reason, we don't have to have values that are above 2. We could have them, but we don't have to have them. So that statement is a false statement. So that's number 5 for you. That was a long explanation of each of those pieces, but hopefully that helped out. Let's go on to number 6 now. Number 6, it gives us the graph of f prime. And it's asking for which f has a relative minimum. So we're going to go a little bit deeper than we were before. Before we were talking about just when is f decreasing or when is f increasing. But here we're looking for when f has a relative minimum. So let's justify it first. F has a relative minimum when f prime changes signs from negative to positive. Okay, so we can explain this pretty easily. If f prime is changing signs from negative to positive, that means that f is going to be changing direction from decreasing to increasing, thus making a minimum of some sort of relative minimum. So we can see that pretty easily in the graph because we were given the graph of f prime. So if we're given the graph of f prime, we can see that f prime changes signs from negative to positive whenever f prime changes from being below the x-axis to being above the x-axis. Again, because this is f prime. If this was f, we would just be looking for low points. We would be looking for when the function changes from decreasing to increasing. But because this is f prime, we're looking for when f prime changes from negative to positive or from being below the x-axis to above the x-axis. So we can see that that happens at x equals -4 and at 0. So we see those 2 points. Then the next question is this, on this particular problem. I would say that there's a little bit of an error in this problem because is this function continuous? Does it continue going on forever outside of the interval that I graphed here? Well, if it does just continue going down, then this is our final answer. But let's go ahead and assume that this graph has endpoints at -5, x equals -5 and x equals 3. Let's just assume that just so we can explain this a little bit further. So I'm going to go ahead and graph this so we can get an idea of what's going on here. We have this guy that does this, let's see, and then it goes back up and then back down again. So let's say that these are endpoints here. Well, at this point, that point is -5, and over here we have 3. So we have the graph of f prime here. What I like to do is look at the number line of f prime. That just helps me see it a little bit better. So I've got -5 as an endpoint here. And then we've got -4. This was -2. We had 0. We had 2. And we had 3. So at all of these intervals here, we've got for f prime, we have a 0 here, 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 and here. And we have endpoints at -5 and 3. So we can see that f prime is negative over this interval here. Let me use a different color. F prime is negative in the interval -5 to -4. It's positive from -4 to -2, negative in that interval, positive in that interval, and negative in that interval. And so we can see if f prime has those signs, then we can see that f is going to be decreasing, then increasing, then decreasing, then increasing, then decreasing. And so we know that we have relative minimums at -4 and 0, and we can kind of visualize it here, right? But we're done with that part. We can see that there's going to be a minimum here and here. But what's happening at the ends? We can see at x equals -5 that the function is here, and then it decreases. So from here, the function decreases, which means this is not a relative minimum, it's a relative maximum. But at the other end, we notice at x equals 3, we have an endpoint here, and the function is decreasing to it, which means it is lower than all the other points immediately surrounding it. So when x equals 3, we actually have another relative minimum. Now the justification for that is going to look like this. We would say since f prime is negative for 2 is less than x is less than 3, f has a relative minimum when x equals 3. So there's our two sets of answers. So in conclusion, we'd say we have a relative minimum at x equals -4, at 0, and at 3. So again, everything we do needs to have proper justification on it. And these are our justifications, not the number line. So that's a look at number 6.